All right, whatever it takes. 0 over 0, right? Undefined. So there's our hole, right? But it looks like as you get closer to 0 from both sides, the function appears to be doing what? Okay, so we want to start talking like calculus students. What is the limit as x approaches 0 of this function? So I'm asking you this. What is the limit as x approaches 0 of this function? 1. Everybody see that? Now you have to, because I did not put plus or minus here, you had to check both directions, didn't you? And it does match. If I'm approaching here 0, right? If I approach from the left, I'm just kind of walking along here. These points are going up, 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 and they're getting closer to a y value of 1. Now when I get to 0, the whole thing falls apart, right? Who cares though? This is a limit. The limit is not asking about what's happening at the point. It's asking what's happening near the point. And then the same thing happens from the right. It approaches a y value of 1. So the answer here is 1. Even though f of 0 is undefined, the limit as we approach 0 is 1. See, you feel better?
Oh,
yeah, good, good. So yeah, that's the most important thing. I won't ever say anything that important. Sorry, bud, you missed it. That's okay, all right.
Yeah, you got the notes.
Okay, you're right. Okay, so does anyone have anything, that I need to clarify on this? Yes.
So when you're giving us problems, are we going to have to graph that function before we figure out the limits?
You're going to have to do a lot of different things. I might tell you, hey, look, draw me a function that does that. So look, yeah, you don't, look, there's something that's going to start to happen, okay, as you progress through your mathematics. It's not going to be just monkey see, monkey do. It's not going to be me up here do an example. Now, you're only going to be asked to be able to reproduce that sort of example. This is conceptual. You have to understand what's going on. So let's do that. Why don't you draw me a function that does that? Okay, I'm going to do that for you right now. Here we go. I have to draw a function that as I approach 0, the limit is 1. So here's 0. I need to approach that value of 1, right? And because there's not a plus or minus, it has to be from both sides. Agreed? So I can do this, and I could do something like that. That would be a function that does that, right? Now, what happens here? It's up to me, right? Because this is the only restriction I have. So I can just fill it in with a dot. There you go. There. That does that, doesn't it? Now, someone else could draw that, and they could decide, you know what? I'm going to be a rebel. And I'm going to do it this way. I'm going to put a hole here, make it go out the other side like that, and then I'm going to actually define it down there. What's that? Whatever I want. Doesn't matter. Right? Do you agree that this picture right here also satisfies this? Yes? So you're going to have some homework problems where they're going to give you a bunch of conditions, about 5 or 6 of them, and you have to draw a function that satisfies all 6. Now I do one of those for you, so that you have that in the video, but the idea here is that, look, you want to take these concepts and extend them into the homework, not looking to just like, man, he never did that one, man. That's the idea. That's the idea. This is a little more than just that. That's why when I turn around, I say, do you understand? You have to ask for any clarification. Ooh, this one's interesting. This is a very interesting function. This is one of the most important functions to understand. Not that you're going to see it all the time, but there's so much happening in this function that it's worth us taking a little time for. We all know what the sine function does, right? Just oscillates, right? Back and forth between 0 and 1. So if I were to ask you to graph just sine, we all know what it looks like. We're all happy. But it's not just sine. It's sine of 1 over x. That's different than just sine x. So I want us to just think about 1 over x for a minute. If I asked you to graph 1 over x, back from college algebra, you might recall that it looks like this. In fact, if you watch the videos for 1.1 and 1.2 that I told you you should watch, I talk about this function. This is what it looks like, right? That's what it looks like. That's what 1 over x looks like. So the interesting, you tell me, what x value does it look like we have something very interesting happening? What x value? 0, right? I mean, it looks like there's some really bad stuff happening at 0. And you can tell where it is here because 1 over 0 is undefined. So we all know from this right here, f of 0 is undefined. I'm going to put UND. Is that okay? UND? That's undefined. My D's look like O's. I'm sorry. So we know we can't plug 0 in. The question is what happens near 0, right? As we come in from the left and the right?
Yeah, it goes 0. Somewhere like that.
I don't know. Can you tell what's happening? Let me zoom in for you. How about I zoom in? Or you know what? Let me come in from the left. Here we go. You ready? Da, da, da. Like that point's real happy, right? It's just like, da, 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 da. Life's good. And then it goes up, and then all of a sudden, in here, things start turning pretty chaotic. So watch this point. I think I can just play this. Uh-oh. Oh, I forgot to press play. Sorry. Here it goes. Oh, that was too fast. There we go. So just watch that point go. Here it goes. So it goes up, and then it goes down, and then up, and then down, and up, and down, and up, and down. I mean, seriously, that's what it's doing, right? Why is it doing that? Why is it doing that? It's because, look at what's happening as you approach 0 from the left here. Where does this function go? Down to where? What's that down there? Negative infinity, right?
Yeah.
Negative infinity. So between here and 0, you're going to take on values that are negative, and they're going to go all the way to negative infinity, which means they're never going to stop, right? So that means as I'm moving over here, this number in here is going to become negatively infinite. What does that mean? That means you're going to try and do all your sine oscillations. You're going to try and do an infinite number of oscillations in this much space. Do you kind of see that happening? Like when you have just sine of x, that's sine x, boring, right? As you go out to the right. So you're going to have one period every 2 pi, right? One period every 2 pi. But when you put this in here instead, you're going to try and have an infinite number of periods in this little tiny section. And so what happens is it goes crazy, as it just did. It starts freaking out. And then when it gets to 0, it's undefined. So, I mean, it's a disaster. This is a disaster. And the same thing happens from the right. And so this one turns out that it's undefined at 0, and the limit from both sides does not exist. That's where we use the word for doesn't. We reserve does not exist for limits. Okay? So if someone's asking you about a function at a specific point, and if it's 0, division by 0, you say undefined. I'm going to write this down.
Is that the only situation where you would say the limit is not exist?
No, there are others. Yep. Okay, so if I write this down, hopefully this will make sense. F of 0 using this function is undefined. If you want, you can write UND. All right? The limit as x approaches 0 of this function does not exist. You may write DNE for does not exist. That's a DNE. I had a student a few years ago that were like, he just kept on writing 1 down. I didn't know why he's writing 1. He just kept on writing 1. It's DNE, not ONE. Does not exist. I will take off on a test if you use those two terms incorrectly. So if you were to, on this problem, if you were to write f of 0 does not exist, I will say that's partially wrong, because I'm not going to be like completely slaughter you with it, be like 0. But we reserve does not exist for limits. We reserve undefined for values of functions at specific points. Okay, is it headed to, as I come in from the left, is it headed towards a specific number? It took off, right? And it just kept going crazy. As we came in from the right, was it headed to a number? It was just oscillating like madness, right? It wasn't headed to something. It has to head to something for me to be able to say the limit exists. I need to be able to put a number in there. And I couldn't put 0 here. I couldn't put 0, because you can't tell me that's approaching 0. Right? This is such an interesting problem because, man, I can't zoom. Oh, here we go. I was like, what? I didn't zoom on this? Okay, there. I'm going to zoom in. Okay, can you see that? I zoomed in, and I'm going to zoom in even more. And at some point, the computer starts to give up. All right? The computer actually starts to give up in here. You can see the jaggedness because it's trying to draw an infinite number of sine curves in a small little gap of a space, and the computer just eventually says, I can't do it. Okay, interesting problem. It'll creep its head out again, all right? That problem, that sort of thing happening. How about this one? What do we end at 12:40?
Yeah, 12:40.
Boy, this class is dragging on. Sorry about that. Sometimes these first classes always just zoom by for me. I know they're probably dragged for you, but this is one of those ones where it's just, we got time, this is good. How about this one? Let's first look at it through the algebra eyes. What's f of 0? F of 0 is undefined. UND, undefined. Now, I'm not talking about what's happening at 1 or at 2 or negative 1, right? Because there's really nothing interesting happening anywhere other than at 0. Do you agree? All right. How about as I approach 0 from the left? It's headed towards negative infinity, right? Now, early in this book, when you get to something in the book like this, early in the chapter, it wants you to say this situation does not exist. That's what they want you to say, because it's not headed towards a number, right? Is infinity a number?
No.
Is negative infinity a number? No. It likes you to say right now that the limit as x approaches 0, how do I say from the left? A little negative there, of the function, they want you to put does not exist, DNE. I, on the other hand, do not like that answer because we're going to change that in the next few sections. And we're actually going to put negative infinity. It is approaching negative infinity. So I'm just pointing that out. If the book says that early on in this first sections, if you put infinity or negative infinity and you're trying to get your answers to match the back of the book, it's going to look different. I want you to put negative infinity here, because that is where it's headed, right? That's where it's headed. Now, what about approaching from the right-hand side? What's the limit as x approaches 0, this time from the right?
It goes just positive infinity.
Positive infinity this time, right? It's different. As I'm coming in this way, it's headed up. What's the limit as x approaches 0 of the function?
Positive 0.
Careful. What do y'all think?
Wait.
Negative and positive infinity?
Look at this right here. What am I asking you for here?
Negative and positive infinity?
Oh.
I'm asking you to look from both sides, right? You shaking your head? What do you think? No, undefined's for function values, but you're almost there. Does not exist. I know you're like, what? Wait, why is this one does not exist? Okay, look. In order for a limit to exist at a point like this, and there's no plus or minus here, from the left and from the right have to go to the same place. They have to go to the same place. From the left, it goes where? Negative infinity. From the right, where does it go? Positive infinity. Negative and positive infinity are on total different areas of the number line, right? They have to go to the same place. Now, if this had been left side it approaches 2, right side approaches 2, then the answer here would be 2.
What if it was like the left side approaches -2, its right side approaches +2?
Does not exist.
So if they're not going to the same, if they're going to their opposites.
They have to go to the same exact value for the limit to exist. Got it?
Just clarifying, yeah.
Mhm.
For the limit of x to 0, it's just going to be like that, and not positive or negative, right?
If it's not written positive and negative, that means you have to look at both positive and negative and make sure they're the same.
Right, I'm just clarifying. I didn't
Yep,
answer that last
that's right.
last week.
And I'm gonna actually summarize this, I think, here at the end. Are there any other questions on this? Okay. Let's see, do I do? Yes, good. This is a good one. One over x squared. Okay, so let's ask the algebra question first. What's f of 0? F of 0, undefined. I'll write it out. Undefined. They both go to the same place, don't they? From the left, this function is approaching positive infinity. From the right, the function is approaching positive infinity. So if I write this down, like that, that would be correct. And that covers both the left and the right, doesn't it? This is telling you, the reader, that for this function, as I approach 0 from the left and right, since I didn't put it there, it implies both, that it's going to positive infinity. That picture matches with this information, right? If I did put a minus here, what would the answer be? Infinity, right? If I put a plus here, what would the answer be? Infinity. So that means you won't need to write plus or minus, just write 0 and it's understood. All right, this is where we get into some, definitions, and not definition, just language, all right? The thing I want to be clear of is when we are dealing with limits, we are talking about what x is doing as we approach a number, as we get near a value, like x was approaching 0, x was approaching 2. We were trying to figure out what the function was doing, right? Everything is using these words near or close, and it's kind of ambiguous. When we approach from one side, one of the sides of the function, one of the following can occur. So if you were trying to figure out what happens from the left, if you're just looking at one side only, you can approach some number, you can oscillate infinitely many times, or it can take off to infinity or negative infinity. Fortunately for us, that's it. That's all it's going to be able to happen in this class. All right? If you're coming in from the left on a function, it's one of these three things are going to happen. Same thing if you come in from the right. One of those three things is going to happen. Got it?
So is it like a rule of thumb if it oscillates infinitely?
That's right. It doesn't exist. Now, I've given a problem like this on a test before, where I had a curve that did something like this. Like that, and I asked for what's going on at 2. Okay, so what's the limit from the left of 2? Let's change that to a different number so people don't confuse it. Let's say that's 3, okay? Right. So what would the limit from the left be there? 3. The right would be does not exist. But I guess if you see oscillations, that doesn't automatically throw out the possibility that you could have a limit on the other side. Okay, so I have here the left limit exists, the right one doesn't. What's happening at 2? Looks undefined. All right, this is just more stuff you can read. We have technical names for approaching from the left and the right. They're called the left and right hand limits. So when you say, hey, let's do the left hand limit, that means you're coming in from this side, you're using the little negative sign. If you say, hey, let's take a look at the right hand limit, that means you're coming in from the right and you're using a little plus sign. Notation, this is all the stuff that, I just said, hey, notice the little negative sign, notice the little plus sign. Remember, you can print all these notes out. It's not, you don't have to worry about copying everything. This is important though. If you don't see a plus or minus sign, what? This means we approach from both sides. It's implied. So it's a very strong condition. If you say the limit as x approaches, let's say 5 of a function equals 10, that means from both sides it's headed to 10. That's understood. I enlarged everything. That's why everything's all jagged. If I put it back to 100%, it'll look cleaner. Let's see if we did that one already. We did that one already. Oh, this was just to show you the notation. Right? See this picture right here? The limit as x approaches 2 of f of x equals 8. That's correct for this picture. From the left, from the right, it's both 8. This one right here, from the right, it's 4, right? From the left, it's 8. This is all just a summary. I have a good feeling y'all understand this, but I could be wrong. Now, there is a more precise definition of the limit that we're not going to touch too deep in this class. Every Cal 1 instructor has to make a decision of how deep they want to get into this idea of the limit. And I take the point of view of, look, most of you will be fine without a precise, really rigorous definition of the limit. If you're a math major, you will have to suffer through that later, and you'll be fine once you get there, okay? But here's the problem that we're running into. Hi. Yes. What's up? Cal 1? Okay. All right. So, no way. Here's a problem. When we've said, like, we started out at the very beginning, we said, okay, here's 2, right? We're gonna approach 2. And I asked everyone to give me a point that was really a number that was really close to 2, right? And I think we started with 1.9, right? And then we got 1.99, and so the idea of closeness is problematic. Because what do we mean by close? If I say 1.9, is that close to 2? Close is relative, right? Close is relative. Like, am I close to SeaWorld? Yes? Am I close to the sun? No? Compared to a different solar system, I'm close to the sun? It's relative, right? Like, is this close? Is this too close for you? This is a little too close? So, like, closeness is arbitrary. We said there's an infinite number of numbers in here, right? So you may think 1.9 is close, and then someone else may say, that's so far away from 2. To me, 1.9999999, that's close. And then you have the ultimate skeptic that says, no, I need like 1,000 nines before I'm happy with the idea of close. And are you ever going to run out of, someone's always going to be able to come and argue, right? Now, as mathematicians, we have a way around that. And it's not cheating, we have to be even more precise in our definition for this. And I'm not even providing you with the strict definition of the limit. It's what, any math majors? It's what you'll get to know is a delta epsilon definition. And we get around it. We get around it. Basically, the way it works is that you, as someone who's trying to prove a limit exists, asks the skeptic for how close they want. And then you go and prove to them that you can get within that closeness. And you can do it for any positive value they ever come up with. So I don't care how close you are, we'll be able to do it. We're going to spare everyone the grief, okay? And I'm almost out of time. Well, I've got 10 minutes. Let's see if there's anything else on the bottom of these notes. Oh, drawing an example. And that'll be it. This will be, okay, I would like for us to draw an example of a function that does all 7 of these things. All at one time. I'm gonna do this one for you, okay? You're gonna go home and do your homework, okay? Your homework will not be as hard as this, but your quiz and exam will be like this. All right, so watch the way I do this. Everyone can get that, right? Okay. All right, so I'm going to just knock these out one by one. How many of these are college algebra things? Oh, wait, there's 2 2s. Oops. There's 2 2s. Sorry about that. Okay, that's college algebra?
Yeah.
That's college algebra. Those are points on the graph. Dots. Where? This? That's a 1. Sorry. No, that's the weird font, I guess I'm in. Okay, so I can actually put this point on the graph, can't I? F of -2 is 0. -2 is my x value. The function spits out 0. Agree? All right, so I've got that. Cancel. All right, next one. F of 1 is 2.
1 there and pretty much.
2 up. Right there. Those points can't be moved. There they are. All right, let's try this first one. As we approach -2,
It's coming from the left.
that's why I gave you this. As I approach -2, the function's approaching 3. Now I need to write that a little different so you can be clear. That's what that first part is, right? Do you see a plus or a minus on the top right corner? No. So it's both. And that always gets people, they think this negative has something to do with the plus or minus left or right side. That's not it. It's -2. That's where you're approaching, right? So I need to draw something so that when I approach -2 from both the left and right, my y value is where? Up at 3. So watch the way I do this. I'm going to do this, I think I'm going to do it in red. Well, I'll do it in black. Okay, so up here at 3, I'm supposed to be getting close to this value, right? Mm-hmm. So I'm going to put an open circle here. And as I come in from the left, I'm supposed to go here, and as I come in from the right, I'm supposed to come in here. So I'm just going to make these little tail edges like that. That's all I'm going to draw. And I'm going to put it all together at the end. But right now, this would satisfy it, wouldn't it? Okay. And if you wanted to, you could have done this. You know, there's different ways. It's all up to you. Could I have filled that in with a solid dot? No, why not?
Because the function of negative.
It's already defined here. And if you define it here again, it fails the vertical line test, right? You'll have 2 points hit by the same line. It's no longer a function. All right.
If we didn't have that -2 down there, then we could have.
You could have left it open. You could have put your own dot wherever you wanted. It would have been, you would have had that freedom of choice there. Okay, that's taken care of. As I approach 1 from the left, I need my function's y value to be approaching -1. Right? 1 from the left. So here's 1 from the left. Means as I come in this way, it needs to be approaching what y value? -1. So down. So I'm going to put a little circle here again like this. Here's -1. And this is approaching from which side? The left. So I'm just going to that's it. That's all I'm drawing. And I'll connect it all in a minute. That all right? How about this.
Let's
Approach
see,
one
it'll be-
from the
yeah,
right.
From the right, and it'll be y up 2.
Y up to, so I need to jump up, don't I? Let's see. As I approach one from the right, I need to be up here too. Hey, well, great. I already have a solid dot there, don't I? I got lucky. I just need to just pop something out the side of that. We still good? Oh, as I approach 4 from the left, I need to go to infinity. 2, 3, 4. Here's 4. So imagine,
Oh, right.
yeah, imagine here's 4, right? This vertical line going through here. I need this function to go and take off to infinity, right? So I'm going to create almost like a vertical asymptote in here. I'm just going to make my graph go up like that. Do you agree that that would follow what's going on right here?
Yeah.
How about from the right, though? Let's approach 4 from the right. The function needs to go to 0.
So just it'll be a 1. An open
So
sign.
4 from the right. Just, you want to do an open circle here? Like that? And then anywhere out here, right? Like this? So as you approach 4 from the left, you're going to infinity. As you approach 4 from the right, it's headed to 0, right? What about a dot? Do you want to put a dot in here? Is it undefined? Ah! I didn't catch that down there. Thank you. 4 is undefined. F of 4 is undefined. So now, this tells you you cannot put a dot in here, right? You don't have that freedom. If that number 7 down there was not there, could I have put a dot here? Sure. Could I have put a dot here?
Yes.
Sure. Could I have just left it like this? Yes, that would still technically follow everything, right? So because of this, I can't fill that dot in. And we're done with this, right? That's it. Now I need to put it all together. This needs to be a nice looking, smooth function, not with all these little gaps and breaks in it. So I think there's some natural things I could do here. Like this, I could just put a little arrow on it like that to say, hey, it just goes like that. And then from here to here, I could just connect these, right? This seems like a pretty natural one here. And then here, I'm just going to do that just to be different, okay? I like to be different.
Yeah, that's practically it.
That function, as drawn, would satisfy all those conditions. Everybody's going to have a different picture, right? Everyone's going to have a slightly different variation, but we should all have the same basic characteristics. We good? Okay, we have 5 minutes, and there was one more thing I wanted to show you. You can start packing up. We have to sign in. Every day we have to sign in. It's a pain in the butt, but it's required by the state of Texas. So you'll see your name, you'll see today's date, just initial into that column, pass it around, make sure this goes around to everyone. So this will be my last little spiel here. Yeah, those little, your schedules that you filled out, those schedules, just leave them on your table. I'll come by and pick them up. Don't, I'll give you one. Okay, so here's what I want to show you because I still have 4 minutes and, you know, it's either your money or taxpayers' money, so we take advantage of it. We were just talking about the number 2 and that number that was closest to 1.9, right? How close it was, and we had the little argument of, you know, someone could say closer. And I know somebody in the back of their mind was thinking about the number 1.999 forever, right? So what's your idea on that number? What are you thinking about that number? Is that the number right next to 2? What do you think? Could be. What do you mean?
Like if we want to compare it close to someone like so 1.99.
This has an infinite number of 9s on it, right? What I'm asking you is, here's the number 2, right? First of all, is there a number right next to it? Right next to, is that the number right next to it?
Yes, could be.
What is your gut telling you? What do you think? Do you think this is the number right to the left of 2? Could be. That sounds non-committal. Okay, so you have your own idea of what it is, right? Okay, I'm gonna show you what it is. You ready?
Yeah.
Okay. I'll do this way. Let x be equal to 1.99 forever. All right? Let's just call that x, everyone. All right? That's x. Everyone happy?
Yep.
Okay. What happens if I multiply x by 10? What's 10x? So what happens when you have a decimal and you multiply by 10? Moves the decimal point one place to the right. So this would now turn into what?
19.9.
19.9, and you have a bunch of 9s there still? On that 9 forever? That didn't change? So if I define x to be this, which you all agreed I could, just call that x. I could call it blue, I could call it green, I could call it a tau, I could call that whatever I want. I called it x. If you take 10 of those, this is what you'd have. Yeah? Now follow this. This is pretty cool. Algebraically, everyone, algebraically, this is not the way we normally write this, but just follow with me. What's 10x's take away 1x? 9x's. Now I'd like for you to look at that in terms of these two things. If this is 10x and this is x, what's 10x? That's 10x. Take away, what's x? What is it? Do y'all follow that? Okay, so I don't know if y'all can see that. Let me put one more 9 out here. Can you subtract these two? Can you tell what's going to happen? What's 19.9999 forever minus 1.9999 forever?
You're gonna have like
The 0.99 stuff should go away, right? And then you have 19 minus 1, which is 18. So look, that means that 10x minus x is 9x. This is 10x minus x. That's 18. 9x must be 18, which means that x must be 2. 1.99 forever is the number 2. Have a good day. There is no number closest to 2. There is no number closest to 2. As soon as you think you found one, you've missed actually an infinite number of them. That's what makes the real numbers so amazing. Everybody is signed in? All right. Do your homework. You should be able to. You're going to pay a lot more for it that way. Yeah.
Yeah, okay. I'm gonna take a picture of it.
Do you have to take Cal too?
Probably, yeah.
Yeah, so you'll be able to at least use it again. Oh, someone's phone. Oh. Okay, this right here, I asked people to fill out. It was just a, like, there's color code down here. Like blue is like when you're in class. Orange is when you're working. Like, I'm just trying to get a feel for everyone's, like, how much they have on their plate.
Okay.
And I also have,
In class.
no, it says it on the bottom. Look, it says it right here. And then there's some highlighter, there's markers right up there.
Should I do that at home, bring it back?
Do you have a highlighter you could fill?
Yeah.
Yeah, sure, yeah.
And do you know what building the bookroom is?
Yes, let me show you.
Okay.
Look, we'll just look out this window.
And it's the only thing that I did, right?
What's that? That? Yeah.